I have a ping pong ball connected by a string to the bottom of this container filled with water. On the other side, I have a solid steel ball the exact same size as the ping pong ball hanging in the exact same amount of water. So when I remove the stopper from the back, which way will the scale tip, if it tips at all? If you think you can answer this, then how about another question? Now I have a steel ball hanging into some water so that the water's filled to 500 milliliters. And on the other side, I have exactly 500 milliliters of water. Which way will the scale tip in this case? To the right, left, or will it stay exactly where it is? Well, let's check what happens in both of these cases, and then we'll talk about why it happened and the weird applications of these physics. Okay, first let's check our initial setup, with a floating ping pong ball on one side and a steel ball dipped in on the other side. Okay, 3, 2, 1. It tipped the way of the steel ball. Is that what you guessed would happen? So if we look at our first setup, let's look at each piece that's on the scale. We have the cup, the water, and the ball. I've just taken the individual components. I have the same exact amount of water and the ping pong ball from the experiment. So together they weigh 532 grams. Even if we assemble it the same way we did in the experiment, it's the same weight. Now let's look at the steel ball side. Now on the steel ball side, we had the same amount of water, the same container, but now I have a steel ball. But unlike the ping pong ball side, we aren't letting the whole ball sit on the scale. We're holding some of the weight of the ball up, so it doesn't sink to the bottom. So let's measure how much of the ball we're actually letting sit on the scale. I'll place the water on the scale and then dip the ball in, and you can see it goes up by about 35 grams. Now the steel ball by itself is way heavier than that. It's about 239 grams. So the amount of weight we put on the steel ball side was the container plus the same amount of water plus 35 grams. So the ping pong ball with the glue on it weighs 3.3 grams. So essentially what tipped the scale towards the steel ball side is that the ping pong ball weighed 3 grams and the steel ball weighed 35 grams, which is just over 30 grams more, so it tipped to the steel ball side. But what's this arbitrary weight that we're getting on the scale when we dip the steel ball in the water? Well, if we look at this weight, it happens to be the exact same weight as a sphere of water the same size as a ping pong ball. For example, I can check this by just filling this ping pong ball with water and checking its weight. About 35 grams. So by dipping the steel ball in water, it's essentially like we replace that steel ball with a sphere of the same size made of water. So why does the weight of the steel ball in the water suddenly become the weight of that same volume of water? Well, we did this artificially by lowering it into the water so that it neither sinks nor floats. This means that we artificially made it have the same weight as the water it displaced. The extra weight of the ball is carried by the supports off the scale. This is just Archimedes' principle that says the buoyant force on an object is equal to the weight of the water it displaces. So we displaced a ping pong ball size of water, so that's how much that weighs. So if you were able to guess what happened in this first experiment, now let's try our second setup and see if you get it right. With the steel ball on one side dipped in the water and pure water on the other side. Okay, 3, 2, 1. It stays exactly where it is. They're perfectly balanced. One side had pure water in it, and if in our minds we replace the dangling steel ball with the exact same size sphere of water, then we see that we end up with the same volume of water on each side, so they of course both weigh the same. So the key to this is that if we from off the scale push into or hang anything into a container of water, it will be the same as if we just replace that same shape with water itself. So if I push a ping pong ball into water so that that level of water is at 500 milliliters, or if I dangle a steel sphere into water filled to that same 500 milliliter level, or if I just have water filled to 500 milliliters, they all weigh the same. This is an important feature. It means that if you have a given volume of water or any liquid, it doesn't matter if you replace that liquid with a boat or a hanging sphere or anything else, it will always weigh the same. So that means if you had a bridge made of water, for example, some aqueduct that was supported from below, you don't have to engineer it for a certain number of boats. You just have to engineer it for pure water. It will never weigh more than that. In fact, there are actually places that have water bridges, and if you know the maximum level of water in that aqueduct, it doesn't matter when a boat goes over the bridge, it will weigh exactly the same. I even tested this at home and cut out a little section of my bridge and put a scale under it, and you can't detect any change in weight when a boat goes over it. But I know that some of you have one little nagging thought at the back of your head still. I showed you that when the ping pong ball was held underwater by a string connected to the container, the whole thing weighed 532 grams. But when I pushed the ping pong ball under the water, it weighed 563 grams. The difference in weight being about a ping pong ball sized volume of water. Why is that? Well, when the ping pong ball is glued underwater in the container, we don't have any external forces pushing on it that can make it weigh more. It's held underwater by its own internal forces. So it's basically like it's part of the container. But when I push the ping pong ball under the water, I'm adding a new force to the scale. I took some of my own weight from off the scale and added it to the ball to make it weigh more until it floated neutrally buoyant in the water. So it matters where the force that holds the ball under the water is anchored. If the string is attached to something off the scale, like your hand or a stand, then the container of water behaves as though the ball were simply replaced with an equal volume of water. But if the string is attached to the container itself, like gluing the ball to the bottom, then the container is directly supporting the extra buoyant force. In that case, the ball effectively becomes part of the container, reducing the true water volume inside, and the scale shows less. By the way, I am aware that Veritasium made a video on this first experiment I showed over a decade ago. And it's a great video, but the explanation for why it happened gets a little bogged down with force vectors. So I wanted to try to explain it in a little more intuitive way for those who couldn't follow that explanation. And thanks for watching another episode of the Action Lab. I hope you enjoyed it. If you did, don't forget to hit that subscribe button, and we'll see you next time.